This class is going to detail on how to apply all those kernels and all those support vector machine versions that we developed together to solve a generic problem, like any kind of classification problem. In fact, I decided to use this data set called Shapes to Moon. This is going to create a more complex data set, and of course that will require a more complex kernel to represent it. And given that problem, we will basically develop another code to evaluate several kernel possibilities and decide on which is the best representation for our input space. I will start opening a new terminal here, R, and then inside R, of course, I will load my code data.r just to show you the data set that I created. This is the data set in green and black. And of course, here we have two, they look like moon shapes or something similar. One like intertwined with the other at some degree, of course. So the best solution would be given by some kernel capable of finding this curve, detaching the black from the green points we have here. I just wrote all this part of my code to prepare this data set. You guys can take a look at this code later and run like command by command and see its effects. That's not important for now. The most important is we've got an input space X and an output space Y as expected. In addition, let me leave here. In addition, we have all those kernel support vector machines with the corresponding kernels. We've got a linear support vector machine, a polynomial version, a radial version, and a sigmoid version. So my idea about this is basically to write some tune svm.r, which is going to be a code to assess all those kernels and find the most appropriate for a particular problem. So my idea is something like this. I will load linear SVM here, of course, the polynomial SVM. All those are our codes developed in the previous classes. Here, of course, the radial SVM. And finally, the sigmoid SVM. You know what? I'm going to write a function here called dataset1, because then you guys can just extend my code, adding up more complex spaces and trying to deal with a different data set. In this particular scenario, I will, inside this function, I will return a list, including, of course, my input space and my class labels. So that's going to be the return of this function. Just to make sure we are on the same page, I will open another terminal, another R instance, load my tune SVM, and of course run dataset1 and saving my result in some variable over here. Just to make sure we've got X, yeah, it is there, and Y, yeah, it is there. Okay. So this is our data set, And here we're going to write together a function to perform the tuning of support vector machines in general, kernels of course, how we are going to come up with a nice space reconstruction to improve our results. So basically, people are going to provide the input space and its output space. Of course, we have to come up with the parameters. One important parameter is a list of the kernels to be assessed. In this scenario, I recommend to assess the linear kernel, the polynomial, the radial, and of course the CMOD based kernel. All those kernels, of course. There is another important point. You probably remember, if I leave this code and I go to SVM linear, you probably remember, where is it? Oh, it's linear SVM. You probably remember that we need to provide some parameters. In case of the linear, there's nothing to provide, just x, y, and c. But of course, we have c to provide. So somehow my tune would also require some possibilities for the cost c. Of course, we could come up with a bunch of values here, like 1, 5, 10, 100, and for example, 1000. So you guys can set up a list of possibilities, and we are going to assess all those possibilities in our code. Okay? That's our cost. Additional parameter. If you take the polynomial support vector machine, you probably remember we need to provide those three parameters: gamma, degree, and coefficient 0. So what I'm going to do is basically this. I'm going to go back here, and I will also create a list of possibilities for each of those parameters. For example, let's suppose people want to try gamma 01, gamma 0.5, gamma 1, gamma 2, and gamma 10, for instance. Okay? And of course, the same happens with the degree of our polynomial kernel. So let's say people want to try a second order, a third order, a fourth, fifth, and a fifth order kernel. In terms of the coefficient, let's try like a homogeneous kernel and a non-homogeneous kernel, just like this. Could be even like a small relevance for that coefficient, but we could also bring a greater relevance. So let's try 4 different values for that. Going to the next, the radial support vector machine requires gamma and c, and both were provided. And lately, sigmoid, that also requires gamma and coefficient, and both, and c, and all 3 are in here. So that's pretty much everything we need. Okay. So what I'm supposed to do now is basically this. If the kernel somehow contains linear, sorry, it's the opposite. If linear is present inside my my sequence or my list, I'm going to perform the optimization for this kernel, for this linear kernel. What should I do in that particular scenario? If I go back to linear SVM, you'll probably remember I will have this function, SVM linear and classify linear. So going back, I have SVM linear to perform the optimization. And that's quite easy to run at this point. I need to provide X, my output space Y, and the cost, of course. And this cost is going to vary, of course, from 1 to the number of possibilities we defined for the cost. Okay? And each of those is going to provide a different support vector machine. But there is something missing here. In fact, to assess a kernel, I should come up with some evaluation methodology, so to speak. For instance, I should select part of my data for training, and of course part for testing. So that is something really important. At this point, I'm going to do like this. Let's define what we call holdout probability equals to, for instance, 75%. So I will do something like this. Take the number of elements we've got in X, multiply by holdout, and you use the ceiling or the upper, the rounded upwards, of course, of that number, just to have an integer number of elements to be sampled, okay, from my data set X, which has a first row and it goes up to the any row element. So that will result in the IDs or row IDs selected to compose my training set. So now I have my training set here composed of those row IDs. And my output space for the training set, which is a vector, also in terms of those row IDs. And of course, for the testing set, I will have something like this. So let's write like this. And this will be the complement. That's why we use minus here. That will take the complement of my sample. This is the sample ID, okay? The complement of it. Now what I will perform is exactly this. Build up a model. This is the model, okay? This is my first model. Now you take this model and perform classify linear. Probably you guys remember there is a function inside linear SVM which is called classify linear. I will copy it and bring it to SVM so we can remember its header, and it will receive the model. Of course, my X and my Y, which here is going to be X train and Y train, of course, because I'm using this training set. And of course, I will pass as argument my model. My X is the training set. Of course, the same happens with my Y, which is also based on my training set. And of course, X new is going to be some query here. What is the query that we'll employ over here? That will be given by the elements composing my test set. So I go from the first to the last element in my test set, And of course, what I expect is something like this. It is basically get my x for testing, which is x test, at the jth row, like this. And I expect a given y, of course, which is this one, y test j. Of course, my classified linear is going to provide some result. So here, I have some observed value for my class y. So if y is equals to the sign of the observed, if it's negative, for instance, or positive, I will increment some variable that I call counter here. Okay? And of course, my counter will start 0. Oops, not count, but counter. So of course now I will have this, which is a testing stage. At the end of my testing stage, I will have my accuracy, which is basically the counter divided by the number of possibilities tested in my scenario. From that, I will save some information over here. So I will have something like model information. This will be a matrix. Inside this matrix, I plan to save something like this. Model information is going to aggregate along the rows, along its rows. Something like this. It will aggregate the model, in this case linear, the kernel, sorry, linear. The cost, which is, of course, in this particular situation, it's cost I, okay, and the accuracy. Of course, we are going to need some additional parameters. Those are gamma, which is going to be null over here, or just NA, not applicable, something like that. Degree, not applicable, and coefficient 0, not applicable when using the linear kernel. What next? Of course, now we have to do the same, but for the polynomial scenario. So we're going to have something like this. If polynomial, if polynomial is in my list of kernels, I should run SVM polynomial. I don't remember its parameters, so I will open polynomial SVM. Those are the parameters. I will copy it like this, go back here, and of course paste, just remember. So I need to change to adapt not just my cost, but also gamma. And gamma will assume a bunch of possible values. The same happens with degree, which is going to assume also a list of values. And coefficient 0, the same. You can notice that at this point, we're going to take a long time to perform all those testing stages. But that is the way to go. So gamma, degree, coef 0, yeah, those are here, gamma, degree, coef 0, okay. So of course I need some force again. So I will add up like 1, 2, 3 more force over here. And of course, 1, 2, 3 ends for my force. I'll just type like this, just an additional space, okay? Just to make it fit my terminal over here, like this. And of course, if this is I, and inside is J, this could be like K, P, and I don't know, L. And of course, here it's not cost, here it's not cost, here it's not cost. Here could be gamma, and here it could be degree. Here it could be coefficient 0. So of course now we are going to have gamma is going to vary in terms of k, degree in terms of p, coefficient 0 in terms of L. And now we are going to add up those variables over here. So in that module information, we're going to come up with some additional information here, including gamma k, of course, degree p, and finally coefficient 0 L. Okay. Now, this is not a linear kernel, this is now a polynomial kernel. Okay. Another important stuff, let me see if this is right or wrong. Oh yeah, not classify linear, but classify polynomial instead. Otherwise, the result will not be correct. That's interesting. So now we've got a way of assessing linear kernels, okay, under different costs. See this, assessing polynomial kernels, of course under several different parameters. That's much more complex, I know. And of course now we've got I'm gonna copy this, bring it down here, and now we're gonna have the radial kernel. Okay, radial kernels also with different parameterizations, but I don't remember the parameters. So let's leave this, go to radial SVM and see. We've got x, y, and gamma and c. So just gamma and c. So of course here, no coefficient, no degree. It's going to be gamma and c. Okay, so just two fourths. Besides, of course, there's one side. So here, we're going to define gamma and no degree, no coefficient, just gamma. This is SVM radial. Okay, and this is not classified polynomial, but this is going to be classified radial. Okay, and of course, now we're gonna have this as radial. There is no information about degree, so degree is going to be NA, and coefficient also NA, like this, okay? It looks good, but we have no idea if it is going to run or not. We're gonna see in a few minutes. So another one, the last one, is going to be our sigmoid kernels. And for sigmoid kernels, we've got, I think we've got gamma and coefficient. Let me see. Let's see together. Oh yeah, gamma and coefficient 0. So I'm gonna copy this for over here, up here, dealing with coefficient 0. Bring it down like this. Of course here. Yeah. And of course that 4 is going to finish here. So now we've got SVM sigmoid, and that will depend on coefficient 0 as well. Yeah, and obviously we have to classify sigmoid. Okay. And by the way, here we're going to change this from radial to sigmoid. Cost is cost, accuracy is accuracy, gamma is gamma, and this is going to be, I think the last one is coefficient 0. I think it's the last one. We're gonna confirm it. In field instance, let's go up like this. Yeah, the last one is coefficient 0. You know what? After computing all that, I suggest us to transform this into a data frame because we can add up some column names. How's going to be those names, and which are going to be those names? The first one is the kernel. The second will be the cost. The third will be accuracy. The fourth will be gamma. Okay. The next one will be degree. And finally, coefficient 0. Okay? And then we're going to get that as a result to understand what is the best kernel for our problem. And you know what's interesting? Knowing the kernel, the best kernel, we have a very good idea about how our input space looks like. Okay, let's try it. You know what? I'm going to close this terminal. Close this terminal just to start from scratch. I will open another one. Open R. Dataset 1 is going to be my dataset. Oh, sorry. I have to load my code to SVM like that and get my dataset. That's my dataset, guys. And now I'm going to test it in my tune. Tune x equals to my dataset x, y equals to my dataset y, and I'm just thinking about using all those default parameters and getting the results as a report. This could be called report. Let's see if this is going to run or it's going to, I don't know, I'm going to get like some issues over here. Of course, I could have written something here, like running linear kernels. Okay, that's going to help somehow. At least we're going to see what's happening. Running polynomial kernels. Of course, next one. Running radial kernels. And finally, running sigmoid kernels. Okay? Let's see. Yeah, it's running, but without any kind of information. But at least we've got those outputs from the package low rank QP, which is our package by choice. I just decided to use it because it solves exactly the same problem of the same SVM, this SVM problem at the end. Okay. We're going to get like some results at the end. Let's wait. This is going to take a few minutes. What is interesting is that now we're going to get a very nice idea about our spaces obtained after kernelizing the input space, after producing a different feature space based on our original input space. Yeah, it's running. It's going to take some time. I know it. Just be patient, please. Okay? Okay. At the end, we're going to have those results and see how those kernels look like for this particular problem. What I suggest you is use this code to test different data sets. Try to come up with a more complex data set and apply this tune function as a way of understanding your input space, as a way of understanding how complex is the classification of your problem. Okay. You see that sometimes it takes like several iterations to perform the conversion, and sometimes it takes like few iterations. Take a look. That's pretty much because of our kernel. In those situations, the kernels were just more adequate to perform the classification task, okay? Just waiting a little bit. Yeah, should have printed out all that information about what is the kernel running at that exact moment, because it would make easier to, I mean, actually not easier, but it would make like just more interesting to it. Because at the end of the day, it takes like forever to run those optimizations because they are not easy at all. They take several iterations, as you can see. And this is interesting because this is not an easy problem to deal with. It's not. I can assure you, it's not an easy problem. Okay, let's wait. Yeah, that's my dog. I know it. Okay, running. Let's see the final results. Another one, 137 iterations. Let's see the next. I think those over here are related, probably 110, probably to the sigmoid kernel, I suppose, okay? Just suppose. Yeah. You know what? I could have defined less possibilities over here, like 110 and yeah, it could be 100 for costs over here. For gammas, it could be, yeah, actually for gammas, we better have like more possibilities. For degrees, we could go up to 4. And for coefficients, I think we could go just for 0 and 0.1. I'm going to open a different terminal here and try to run now, just to see how it is going to behave. Loading my data set. That's my data set. You guys remember? This is tune in terms of my data set X, and Y is going to be dy. And I will get my results over here. Okay. Running linear kernels. We can see the results. It's running. So linear kernels. Yeah, it takes forever, I know it. Yeah, here. Linear kernels. Yeah, the first one. Yeah, it's just faster here because it ran already a list of possibilities in this first terminal. I know. Let's wait. So at the end, we're gonna have information on this. Guys, I think I'll just stop recording and get back when this finishes. Okay? See you in the next video.